Welcome everyone. Today we'll explore principles of vibration, waveforms and metrics, fundamental concepts of oscillations and measurement techniques. Understanding vibration, importance of vibration analysis. Vibration refers to the oscillatory motion of an object about its equilibrium position. It is a fundamental concept in mechanical engineering, physics, and structural analysis. Vibration can occur in solids, liquids, and gases, but in engineering contexts, it is most commonly associated with mechanical systems such as engines, turbines, and rotating machinery. The study of vibration is crucial because excessive vibration can lead to fatigue, noise, and failure of components. Vibration analysis helps in diagnosing machine health, predicting failures, and improving design for durability. The principles of vibration involve understanding forces, displacement, velocity, and acceleration, as well as how these parameters interact over time. Vibration can be free or forced, damped or undamped, and linear or nonlinear. Free vibration occurs when a system oscillates without external force after an initial disturbance, while forced vibration happens when an external periodic force drives the system. Damping is the mechanism that dissipates energy, reducing amplitude over time. Understanding these principles is essential for engineers to design systems that minimize harmful vibrations and optimize performance. Vibration analysis is a critical tool in predictive maintenance and quality control. It allows engineers to detect imbalances, misalignments, bearing failures, and other mechanical issues before they lead to catastrophic breakdowns. By monitoring vibration signatures, industries can schedule maintenance proactively, reducing downtime and costs. Vibration analysis also plays a role in product design, ensuring that components can withstand operational stresses without resonating at harmful frequencies. Resonance occurs when the natural frequency of a system matches the frequency of an external force, leading to large amplitude oscillations that can cause structural damage. Therefore, engineers must calculate natural frequencies and design systems to avoid resonance. Additionally, vibration analysis improves safety by preventing accidents caused by mechanical failures. It is widely used in sectors such as aerospace, automotive, manufacturing, and energy. Understanding vibration principles and metrics enables professionals to interpret data accurately and make informed decisions about machine health and structural integrity. Types of waveforms, interpreting waveform characteristics. Waveforms represent the time domain view of vibration signals and are essential for understanding the nature of oscillations. Common waveform types include sinusoidal, square, triangular, and complex signals. A sinusoidal waveform is the simplest and most fundamental, characterized by smooth periodic oscillations. It is often used to represent idealized vibration in theoretical models. Square and triangular waveforms are less common in mechanical systems but may appear in electronic or control signals. Real-world vibration signals are typically complex, consisting of multiple frequencies and amplitudes combined. These signals can be analyzed using Fourier transform to separate them into individual frequency components. Waveforms provide insight into transient events, impacts, and irregularities that may not be evident in frequency domain analysis. For example, a sudden spike in a waveform may indicate a mechanical impact or fault. Understanding waveform characteristics helps engineers diagnose issues and design systems to mitigate harmful vibrations. Interpreting waveforms involves analyzing amplitude, frequency, and phase relationships. Amplitude represents the magnitude of vibration, which correlates with energy levels in the system. Frequency indicates how often oscillations occur per unit time, and phase describes the relative timing between multiple signals. In vibration analysis, waveform shape can reveal specific fault conditions. For instance, a repeating spike pattern may suggest gear tooth defects, while irregular oscillations could indicate looseness or imbalance. Engineers often use time domain plots to observe these patterns and correlate them with machine behavior. Advanced tools allow zooming into waveform segments to identify transient events such as impacts or shocks. Combining waveform analysis with frequency domain techniques provides a comprehensive understanding of vibration phenomena. This dual approach ensures accurate diagnosis and effective corrective actions. Overall levels and RMS, peak, peak-to-peak, and crest factor. Overall vibration levels provide a single value representing the general intensity of vibration in a system. This metric is useful for quick assessments and trend monitoring. RMS, root mean square, is a statistical measure that represents the effective value of a varying signal. In vibration analysis, RMS is widely used because it correlates with the energy content of the vibration. RMS is calculated by squaring the instantaneous values, averaging them over time, and taking the square root of the result. This method ensures that both positive and negative oscillations contribute equally to the measurement. RMS values are particularly important in assessing fatigue and wear, as they reflect the continuous energy acting on components. Monitoring RMS levels helps engineers detect gradual deterioration and schedule maintenance before failures occur. Peak value represents the maximum amplitude of a vibration signal, indicating the highest stress experienced by the system. Peak-to-peak measures the total range of oscillation by calculating the difference between the maximum positive and maximum negative amplitudes. This metric is useful for understanding the full extent of vibration excursions. Crest factor is the ratio of the peak value to the RMS value and provides insight into the waveform shape. A high crest factor indicates the presence of sharp transients or impacts, while a low crest factor suggests a smoother, more uniform vibration. These metrics complement each other in diagnosing machine conditions. For example, a machine with normal RMS but high crest factor may be experiencing intermittent shocks, requiring further investigation. Understanding these metrics enables engineers to interpret vibration data accurately and implement targeted corrective measures. Real-world examples and diagrams, summary and best practices. In practical applications, vibration principles and metrics are visualized using diagrams and plots. Common diagrams include time domain waveforms, frequency spectra, and RMS trend charts. For example, a sine wave diagram illustrates basic oscillatory motion, while a complex waveform plot shows real machine vibrations with multiple frequency components. RMS trend charts help monitor machine health over time, indicating gradual wear or sudden faults. Peak and crest factor values can be displayed alongside waveforms to highlight transient events. Engineers use these visual tools to communicate findings effectively and make informed decisions. In industries such as aerospace and automotive, vibration diagrams are integral to design validation and quality assurance. By combining theoretical principles with practical visualization, professionals can ensure reliability and safety in mechanical systems. To effectively manage vibration in mechanical systems, engineers should follow best practices such as regular monitoring, comprehensive analysis, and proactive maintenance. Understanding waveforms and metrics like RMS, peak, peak-to-peak, and crest factor is essential for accurate diagnosis. Visualization tools, including diagrams and trend charts, enhance interpretation and communication. Avoiding resonance through proper design and material selection is critical for preventing catastrophic failures. Implementing predictive maintenance strategies based on vibration analysis reduces downtime and extends equipment life. By applying these principles consistently, industries can achieve optimal performance, safety, and cost efficiency.